Hello everyone, my name is Karanpal and I am a second year student of Data Science and AI. So today we will discuss a topic of linear algebra which is basis, and we will see that how we can define or do the calculation of change of basis. So let us define the basis. What are the bases? So basis basically a set of the vectors. So the collection of this vector is called the basis set. So the element of this basis set are called the basis vector, and this basis vector should fulfill these two conditions, which are first condition is that they should be linearly independent to each other, and the second property is that they uh, that for any vector in V, we can represent that vector as a linear combination of this basis vector. So which is uh, definition of spanning. So we can also see that the set B is also a spanning set of V. So and the number of the basis vector or the cardinality of this basis set is also called the dimension of vector space V. And what are the standard bases? These are very useful, most frequently used in the linear algebra, especially. So if we have a vector space of dimension n, so the standard basis of this vector space can be seen as the column of the matrix, the identity matrix of the dimension n cross n, where n is same as the dimension of the vector space. So here you can see that the standard bases are going to be the column of the identity matrix, and this is going to be formed some identity matrix of the order same as the dimension of the vector space. So now we will come on coordinates. So what are the coordinates? Uh, to represent any vector in the vector space, let we have a vector u in the vector space V. So we can write this vector u as the linear combination of the basis vector. So the coefficient here used to form the vector u, that is a1 time the basis vector v1 and a2 time basis vector v2 and so on. So these coefficient are called the coordinate of that vector in that vector space using the basis vector v1 v2 and so on. So for example, uh, the coordinate of vector, we are interested to find the coordinate of this vector, which is 2 5. So if we take the basis as the standard basis, so what will be this uh, coefficient? So as you can see that, and standard basis will be a1 into 10 plus a2 into 01. So then we will find that a1 is 2 and a2 is 5. So the 2 comma 5 is the coordinate of the vector u in the standard basis. And for example, if we change our basis from not, if we not take the standard basis, and let we take the v1 equals to 10 and this 11 as the basis vector, so then we will find that minus 3 comma 5 is the coordinate of this vector. So here you can see that if we change the basis, we will obtain a different coordinates. That means, but u vector is fixed, u is both. Here you can see that u, we are not changing the vector at all. What we are changing the basis. So if we are changing basis and u is fixed, obviously this coordinate will also be changed. So that was little about coordinates. So here you can see that uh, we have taken an example of vector a plus b. So this is the most simple vector space, Euclidean R2 space. So here, let this is vector a, this is vector b. If we add, we will get a plus b. So in Cartesian coordinate system, we can see that if this a vector has two component a1 a2 and b1 has b1 b2, so after adding we will get a1 plus b1 and a2 plus b2 as the components of vector a plus b. So if we take standard basis, that means 1 0 0 1, so we will find that the coordinate of the vector a plus b are a1 plus b1 a2 plus b2, which is also visible in this figure. So what will happen if we change our basis? If we not take the basis along x-axis and y-axis, instead of it, if we take the basis as a and b, as you can see that these two are linearly independent, and these we can span entire space R2 by using these two vectors. So what will be the coordinate of this vector a plus b if we take the basis a plus b, if we take the basis as a comma b? So that you can see that a plus b can be written as 1 into a, which is our first basis vector, and 1 into b, which is our second basis vector. So the coordinate here are used 1 into 1. So coordinate of a plus b if we take the basis a comma b are 1 comma 1. So idea here is that how the coordinate are changing. So our problem is that if we change the basis, how we will find the coordinate of the same vector. If we know the, here the problem was that if we know the coordinate in the one basis system that we have taken as standard basis system in this example, how we will find the coordinate if we change the basis? So this is our main motive of this discussion. So now instead of simple doing that no multiplication and addition, we can use the a tool matrix representation of the linear combination. So as you have seen that we have written the vector u as the linear combination of this basis vector. So which you can see that the basis vector are represented as the columns of this matrix B, which is also called the basis matrix. So the columns of basis matrix are the basis vector, and these basis vector are linearly independent to each other. So this B should be, or this is a invertible matrix, and X, which we have used as the coordinate matrix. You can see that this multiplication and addition operation can also be represented as the matrix multiplication in this sense. So for example, the vector that we have used in last example was 2 into 5. So in the basis 1 1 0 and 1 1, this linear combination we also can write as this multiplication of these two matrices. The first matrix here is the basis matrix. In this basis matrix, the columns are the basis vector, and the other this matrix is the coordinate matrix. So up to this we have seen that to find to find any vector u, we need to multiply it by the basis matrix in which the column are the basis and the coordinate corresponding to that basis. Also, if we are interested to find the coordinate of any vector u uh, in the basis matrix B, we need to multiply the inverse of the basis matrix with that vector. So this will give us the coordinate of uh, the vector u in the basis taken as the column of the inverse of this matrix. You can see that if uh, if I multiply any matrix M to a matrix to a vector, let's say A. So what does this multiplication do? This will give us the coordinate of the vector A in the basis matrix M inverse. So here you can see that as the inverse of this B is the inverse of matrix B is B. So this is giving us the coordinate of the vector u in the basis matrix as the inverse of this matrix. And also there is a property that the coordinate of any vector in any vector in the any basis are unique. So why this is unique? That as you can see, the columns which are the basis of the vector space are linearly independent to each other. So that's why this matrix has to be a invertible matrix. So that's why this equation has to be a unique solution. So that's why coordinate of any vector is unique. So now we will discuss about that how we can find the coordinate of a certain vector if we know its coordinate in some another basis sets. So let we have given a vector u, and we are also given its coordinate in the first basis. Let's say b1, which are x1 are the coordinate of the vector u in the basis b1, and we need to find its coordinate if we change the basis from b1 to b2. So how we will do it? As you can see that the vector is same in both the bases. Either you can write in the b1 basis or b2 basis, but the vector will become same, and that's why we can equate these two matrix multiplication b1 x1 and b2 x2. And if we are and if let we know that the coordinate of vector u in b1 basis that are x1, and we need to find the coordinate in basis b2 which is x2. So we need to multiply this both side by inverse of this b2 matrix. So that will give us the coordinate of vector u. You can see that this vector is u, b1 x1 is u vector. So as we have discussed earlier that to find the coordinate of any vector we need to multiply it by the inverse of the basis matrix. So here you also can see that this matrix b1 x1 is u. So that's why this is giving us the coordinate of the vector u in the basis b2. Also here the this matrix is working as the change of basis matrix, because this is changing the coordinate of a vector in one basis to the coordinate in the another basis. So that's why this also referred as the change of basis matrix for the basis b1 and b2. So let's discuss about the orthogonal basis. What the orthogonal bases are? The bases which are orthogonal to each other. That means if we take the dot product of any two bases, the inner dot product of any two basis vectors, if that becomes 0, so the bases are called the orthogonal basis. And the metric corresponding and the basis metric corresponding to that orthogonal basis are is called the orthogonal matrix or the orthogonal basis matrix. So what is the benefit of taking the orthogonal basis is that uh, the computation of the inverse is very easy in the case of orthogonal matrix. The transpose of the orthogonal matrix is the inverse of that matrix. So in order to find the coordinate of any vector u in the orthogonal uh, basis matrix, let's say A, we need to simply multiply the transpose of the matrix with the vector whose coordinate we are interested to find. So that's the benefit uh, as compared to any arbitrary basis, that if we have the orthogonal basis we can easily find the inverse, and thereafter we can find the coordinate of that vector. To be very simple, as you can see that if the b2 is orthogonal, so to find the coordinate x2 in the basis b2, we have to take the inverse if we have not orthogonal matrix. But if we have orthogonal matrix we can take simply transpose, which is also equal to the inverse. So we will easily can find the coordinate of any vector in that orthogonal basis. So for example, if we are interested to find the coordinate of this vector, which is 1, 2, 3, in the basis 1, 1, 0, 1 minus 1, 0, and this, and but the problem here is that this vector is, the element of this vector are given in the basis this. So we will simply uh, use this equation, which is, to find the x, we will take the transpose of the basis in which we are interested to find the coordinate. So here we have taken the transpose, and then the basis in which the vector is given, which is, and that basis vector have the column as this basis vector. So we will simply, this is matrix multiplication, which will order of n cube if we have n element. So that's not higher than the taking the inverse of a matrix. Now we will see some applications of the concept change of basis. So in PCA, which is principal component analysis, uh, our goal is to reduce the dimension of the data. So how change of basis work in this? That for example, if a data is given in the two dimension, so we need to project this data on the different bases, so that uh, the basis which is here, the PC1 and PC2, the PC1 will be the most representative of this data, and PC2 will be some lesser representation of the data. So here we can choose that the PC1 as the most representative of data, so we can neglect this component. So these were, after neglecting PC2, we will get the data in one dimension if we have the original data in two dimensions. So what if somehow we need to find the new data in the basis taken as PC1 and PC2. So as the change of basis matrix, here will be the new matrix inverse, which is take the PC1 and PC2 as the basis vector and take it transpose. Why? Because these are the orthogonal bases, and the data which was there in the two dimension. So hence we can find the data in the new basis PC1 and PC2. So now we will see an application of the change of basis, that how change of basis can help us to visualize the complex transformation done by any matrix, any arbitrary matrix, rectangular matrix M. So we can see that if we direct multiply any vector to M, so this will transform from these kind of things to this kind of transformation, which is very complex to see directly. So we can see by this step by step that how this transformation is going on. So we decompose our matrix in the three matrices, where the first U and the V matrices are the orthogonal matrices containing the eigenvectors of M transpose and M transpose M as the columns. So as you can see that the matrix, if we multiply vector to matrix M, so this will first will go to the matrix V transpose. So since V transpose is the inverse of V, and V transpose is also orthogonal matrix, so we can see that the transformation that will done by this matrix V will be a rotational transformation. So this vector will rotate according to this matrix, because this matrix V transpose is also a orthogonal matrix. And after that we get this new vector V dash. Let call this any Y dash. So this Y dash will be multiplied by this matrix sigma, which will reduce its dimension, or it will project on the uh, some lower dimensional plane, uh, and also scales the axis, or the coordinate along the axis. So anyhow this will project on a lower dimensional plane. and after that the orthogonal matrix U will also come in role, and then when this vector will multiply by the orthogonal matrix, this will rotate it by keeping the angle between the axes which were used earlier, and the um, the basis taking as the eigenvectors of mm transpose, which are the column of U, because U is the orthogonal matrix and uh, we are multiplying the orthogonal matrix, so that will rotate the vector v. So we can see that we can easily visualize these kind of transfer the complex transformation done by any arbitrary matrix by step. And the basic idea here is that we are decomposing our matrix such that we can easily visualize the that how these basic matrices will work on the vector. So these are all can be seen as the change of basis, because here we are simply changing our basis by multiplying the change of basic matrix, which is also a orthogonal matrix. We can say that we are transforming from one orthogonal basis, which is our usual xy basis, and to the another orthogonal basis, which are our eigenvectors of this matrix m transpose m. So hence we can see these kind of complex transformation by changing our basis.